magnetic effect shown by the Earth or the Earth's magnetism. Our magnetic compass consists of a magnet, and it is based on these two things to give us a directional reference. So understanding these two provides us the basis on which the magnetic compass functions. So let's first go into the basic concept related to magnetism. Magnetism is a physical phenomena by which some materials like iron, nickel, and cobalt are attracted towards magnets. These materials which are attracted towards a magnet are also known as ferromagnetic materials. Now, these materials can be converted into magnets themselves also. And to convert these ferromagnetic materials into a magnet, we can use two different methods. There are two techniques or two methods which are available to us to convert a ferromagnetic material into a magnet. These two methods are number one, permanent magnetism, or by use of permanent magnets, and number two, induced magnetism, that is through the presence of a magnetic field. We will discuss both these techniques, both these methods by which these ferromagnetic materials can be converted into a magnet one by one. So beta, everybody is okay. Are you able to see the slide, hear me speaking, especially the new joiners?
Yes, sir.
Yes, sir. Yes, sir.
Okay, beta. All right. Great. Moving ahead then.
So you will be providing us with all these notes.
Let's first discuss the first method by which we can convert a ferromagnetic material into a magnet. The first method is by use of permanent magnets. Now, for making a magnet from a ferromagnetic material by using a permanent magnet, the material like iron is stroked in one particular direction. As you can see in this diagram, we have a iron bar. This is a non-magnet. This is not a magnet. This is a simple iron bar, and we want to convert it into a magnet. So what we do is we get hold of a permanent magnet. You can see the rod which is held in the hand is a permanent magnet, and then we move that permanent magnet in a particular direction. You see the dotted line with the arrows shows the motion of the permanent magnet, and we are stroking this iron bar in this particular way repeatedly. Now, once you repeat this process at least 40 to 50 times, the iron bar then starts to behave like a permanent magnet itself, and it starts showing the magnetic properties. So using this method, you can convert a ferromagnetic material into a magnet, and this magnetism which is acquired by the material then is permanent magnetism. What do we mean by permanent magnetism? Permanent magnetism means that after this process is done, after that, even if you remove the parent magnet which was used to magnetize the iron bar, if you remove it and take it away, the iron bar will continue to behave its magnetic properties. It will continue to show or exhibit its magnetic properties. Now that magnetism has been permanently acquired by the iron bar, and it is called as permanent magnetism. So Let's now go into the second method, which can be used to make a magnet or to convert a ferromagnetic material into a magnet. This method is known as induced magnetism. So magnetism can also be generated by placing a ferromagnetic material in a magnetic field. Now, as you can see in this particular diagram, we have some iron nails and some of the paper clips which are clinging or they are attracted toward this bar magnet. All the iron nails and paper clips actually have become magnets here, which are attracting other nails and paper clips close to them. If you look carefully, the first nail closest to the magnet or the first paper clip closest to the magnet is attracted towards the permanent magnet. But all subsequent paper clips or all subsequent nails have also started showing magnetic behavior because these are attracting other nails under them. So these have started showing magnetic behavior because of the presence of a magnetic field. If the magnetic field is removed, the magnetism of the nails as well as these paper clips is going to disappear and all the nails and paper clips are going to fall down. So this kind of magnetism is known as induced magnetism and it is generated by the presence of a magnetic field. If we place a ferromagnetic material in a magnetic field, it starts behaving like a magnet. Now going a little more deeper into the induced magnetism, the strength of the induced magnet, that means how powerful or how strong this nail magnet will be, depends upon two factors. What are these two factors? One, the strength of the inducing magnetic field. That means how powerful this parent bar magnet is. The more powerful this magnet, the more powerful will be its magnetic field, and the more powerful induced magnet will the nail become. Or in other words, stronger the inducing field, stronger will be the induced magnet generated. And the second criteria which decides what will be the strength of a induced magnet is the alignment of the ferromagnetic material with the magnetic field lines. If the ferromagnetic material is perfectly aligned or it is perfectly in line with the inducing field, there will be maximum induction occurring, resulting in a strong induced magnet being generated. And if the material lies perpendicular to the inducing field, there will be negligible induction resulting in a very weak magnet. This will become more clear to you as we go into the details of magnetism further in the coming slides. But for now, just remember that if the material is aligned with the magnetic field, maximum induction is going to occur. And if the material is not aligned with the magnetic field lines, that means it is at right angles to the magnetic field lines, there will be negligible amount of induction resulting in a very, very weak magnet. Now, once a magnet is generated, either by using a permanent magnet or by using a magnetic field, making it an induced magnet, once it is made, it acquires two poles. The poles are indicated as red pole and the blue pole. So you can see in this diagram, we have a bar magnet having these two poles. the red pole and the blue pole. Along with these poles, it will also generate a magnetic field around it. You can see these dotted line extending out of the physical body of the magnet. These dotted line represent the magnetic field of this magnet. Now these lines, the dotted lines which represent the magnetic field of the magnet, are called as the magnetic lines of force. Any magnet, whether permanent or induced, will have these magnetic lines of force around it. Now the lines of force, they always come out or they originate from the red pole of the magnet. They come out or originate from the red pole of the magnet, and they re-enter into the magnet through the blue pole. As you can see, the right side of this magnet is red pole. It has the red polarity, and you can see all the magnetic field lines or magnetic lines of force are coming out from here. And the left side pole is the blue pole of the magnet, and you can see that all the magnetic lines of force are re-entering into the magnet through the blue pole. So this is a very important property of the magnet. Once it acquires two poles, the red and the blue pole, the magnetic lines of force will always come out of the red pole, and the magnetic lines of force will re-enter into the magnet through the blue pole. Now, in previous discussions on magnetism, you may have also heard the poles being referred to as North Pole and the South Pole, but that will be not correct. The terminology is not correct. Why it is not correct? Once I explain to you the magnetism of the earth, it will become very clear to you that marking the poles of a magnet as north and south is sometimes confusing. So refrain from giving the names as north and south. We will just mention the poles of the magnet as red pole and the blue pole, and we will remember that magnetic lines of force always come out from the red pole and they re-enter the magnet through the blue pole. Okay, up to here, beta. चलें आगे.
Sir, in this diagram, what is the N and S stand for? This is north and south, right?
I've just mentioned it here to emphasize that the two types of magnetism, that is permanent magnetism and induced magnetism. We now go into the properties exhibited or shown by magnets. Now magnets show two distinct properties. These are, number one, a freely suspended magnet aligns itself with a magnetic meridian, with the red pole of that magnet towards the north magnetic pole of the earth and the blue pole of the magnet towards the south magnetic pole of the earth. This is the first property. Freely suspended magnet aligns itself in the magnetic meridian or towards magnetic north and south. Red end points towards magnetic north and the blue end points towards magnetic south. The second property which the magnets show is the unlike poles of magnets attract each other and the like poles of a magnet repel each other. If you bring close a blue pole to blue pole, there will be a repulsion. You bring close a red pole to red pole, there will be a repulsion, a repulsing force. But if you bring the opposite poles close to each other, blue close to red, there will be attraction between them, a attractive force appears, and they are attracted towards each other. So these are the two basic properties exhibited by the magnets.
Sir, one question.
Go ahead. Now we go into one more very important property of a magnet. Now, every magnet is going to have a magnetic field around it. In the area surrounding that magnet, there will be a presence of a magnetic field. Now, the strength or power of this magnetic field is not uniform at all the locations around the magnet. The strength or power of this magnetic field keeps on changing depending upon the location. Now let us try to understand how this power of the magnetic field or strength of the magnetic field varies. Now we can see a bar magnet here in the diagram. If we draw a line joining both the poles of the magnet and extend that line, this is known as the axis of this bar magnet. And any position in the direction of the axis of the magnet is known as a end-on position. You can see it here also. End-on position means along the axis of the magnet. And if you go perpendicular to the axis of the magnet, we go in a direction perpendicular to the axis of the magnet. This is known as broadside on position, exactly like a ship. If you extend the 4.5 line and if you have any target there in that location, it's called as end on. And if you draw a imaginary line around the beam of the ship in the outward ship direction, that's called a broadside on position. So same way, perpendicular to the axis, any position here is known as a broadside on position. So you can see it here. It is at right angles to the axis of the magnet. Now, how does the strength of the magnetic field vary? The magnetic field strength in the end-on position is twice the field strength in the broadside on position. Just to give you an example, if you go 1 centimeter away from this pole of the magnet and measure the magnetic field strength here, and the same thing is done at broadside on position. You go 1 centimeter away in the broadside on position and measure the magnetic field strength here, you will see that the field strength at end on position is twice as powerful as compared to the field strength at the broadside on position. So doubts beta, any Earth's magnetism. Now nature has made the earth as a magnet. Earth has its own magnetic field. We can experience that magnetic field, and this magnetic field is very much similar to the magnetic field of a bar magnet. So let us try to understand the orientation of this magnetic field of the earth. So the magnetic field of the earth is identical to the field of a short bar magnet, as if God or nature has put this short bar magnet and fitted it inside the earth. How is this bar magnet fitted inside? This is shown in this particular diagram. You see, and the magnetic field of the earth is such as if there is a powerful short bar magnet. You see this bar magnet, the blue end on the top and the red end at the bottom. So the magnetic field of the earth is exactly like the field of a short bar magnet. So you can see the red end of the magnet, the magnetic field lines come out of it, and these arrows made on the magnetic field strength lines, they show that all these magnetic field lines are coming out from the red end and they are re-entering into the Earth's bar magnet from the blue color end. If you extend the axis of this short bar magnet, you see this yellow color line extending outside. Wherever this line extended meets the surface of Earth, it meets at this particular point, which is close to the North Pole. It is known as the magnetic North Pole. And if you extend the axis of this bar magnet on the other side, you see here it is meeting up on the surface of Earth, and this is the magnetic south pole. So the short bar magnet is fitted inside the Earth. The magnetic field is exactly similar to as if the short bar magnet is fitted inside the Earth. And if we extend the axis at the points where they cut the surface of Earth, these points are known as the magnetic poles. If you extend the axis close to the axis towards the top or towards the north side, you get the magnetic north pole, and when you extend it towards the bottom or towards the south side, you get the magnetic south pole. Now, along with these poles, you also see a green color line shown in the diagram. Now, this green color line is the axis around which the Earth rotates. Now, this line is different from the line which is showing the magnetic north poles. The green color line, which is the axis around which the Earth rotates, if you extend this line to the surface of Earth, the points where it meets the Earth's surface are known as the geographic poles. So you see, this is the geographic north pole on top. And if you extend it onto the other side, this is the geographic south pole at the bottom. Now, you can also see here that the magnetic poles are not exactly at the same location where the geographic poles are. They are situated at slightly different locations. They are close, but they are not exactly at the same location. The geographic north and south poles are at a different location, and the magnetic north and south poles are at a different location. So as far as this short bar magnet is concerned, the blue pole of this short bar magnet points close to the Earth's north geographic pole, and the red end or the red pole of this bar magnet points close to the Earth's south geographic pole. Any You can see the Earth's magnetic field in a different diagram now. Again, the same thing is represented here. You can see the geographic north pole of the Earth. This is the geographic north pole. This line, the solid white color line, represents the axis around which the Earth rotates. You can see these arrows indicating the direction of rotation. So extended on this side, this is the geographic south pole. The magnetic field of the Earth, the magnetic poles, they point in different directions. The direction in which the magnetic poles point is denoted by the dotted line. So you can see this dotted line extending onto both the sides. The end or the pole which points close to geographic north pole is called as the north magnetic pole, and the end or the pole which is close to the geographic south pole is known as the south magnetic pole. Okay, so this is the same diagram. Let's proceed ahead. So once again emphasizing, the geographical poles are the points where the axis of rotation of the Earth pass through the Earth's surface. The solid line, as I told you before, represents the geographic poles of the Earth. And the direction in which the magnetic poles point are called the magnetic north and the magnetic south. You see the short bar magnet of the Earth. Wherever the poles of this the bar magnet point, these are known as the magnetic poles. So as we have seen in this diagram, the magnetic poles are slightly away from the geographic poles. Now we have seen two different types of poles, the geographic poles where the axis of rotation of the Earth cut the Earth's surface, and the magnetic poles, which depend upon the magnetic field of the Earth. Now, out of these two poles, the magnetic poles of the Earth are not stationary. The geographic poles are stationary, they are at a fixed location, but the magnetic poles of the Earth are not stationary and keep on changing their position or location slowly. Now you can see this particular diagram. The apex of the cone here, this particular point represents the north geographic pole, and this particular diagram, a particular sector of the Earth, shows us the movement of the north magnetic pole over the years. You can see how the magnetic pole has been changing its location from 1600 to 1700, 1800, 1900, and 2000, and so on. So clear, beta? Any doubts up to here? Another diagram which you see on the screen now, showing you the Earth's magnetism. You can see this is the place where the north magnetic pole is, where this red arrow is pointing into the surface of Earth. The point where this red arrow is coming out is the south magnetic pole of the Earth. And you can see the geographic poles also. The dotted line represents the axis, and this is the geographic south pole, and this dotted line going on top, this point here represents the north geographic pole. Now another important thing to understand here is the north and south geographic poles are diametrically opposite points, very much symmetrical, diametrically opposite point, and exactly midway between both the geographic poles we have the equator. You see this straight line represents the equator. Every point on equator is 90 degrees away from both the poles. Now in a similar fashion, we have the north magnetic pole as well as the south magnetic pole. Now north and south magnetic pole may not be diametrically opposite. They do not follow symmetry. They may not be diametrically opposite point, number one. And number two, the magnetic equator is also not a perfect great circle. You see this curved line which is shown in the diagram is the magnetic equator, and this magnetic equator, as you can see, is not symmetrical. It is not a perfect great circle. It's a curved line moving over the surface of Earth, and it does not follow symmetry. Every point on the magnetic equator is not 90 degrees away from the poles. So magnetism is something which is dynamic and does not follow geometry. So let us now go through some basic definitions related to the Earth's magnetism. First we come to the magnetic poles. What are these magnetic poles? Magnetic poles are defined as those points where the Earth's magnetic field lines are vertical. Vertical means perpendicular to the Earth's surface. You see right now where the laser pointer is, this is the north magnetic pole, and you can see that the magnetic field line is vertical here, going down vertically into the Earth surface. Similarly, if you come to the south magnetic pole, the laser pointer is right now at the south magnetic pole, and you see the magnetic field line is coming vertically out from this particular point. So magnetic poles are the points where the Earth's magnetic field lines are vertical. They are making a right angle to the surface of Earth. At south magnetic pole, they are coming vertically out, and at the north magnetic pole, they are going vertically in. Why are they coming out of the south magnetic pole? Because we know the Earth's south magnetic pole has a red polarity, And we know magnetic field lines always come out of the red pole of a magnet. Why the lines at north magnetic pole going into the Earth's surface? This is because the Earth's north magnetic pole has a blue polarity, and we are aware that magnetic lines of force re-enter into the magnet at the blue end. Let's now move on to the magnetic equator. As you can see in this diagram, this random line marked by the highlighter, the laser pointer right now, is the magnetic equator. Now, what is this magnetic equator? It is an imaginary line joining those points where the Earth's magnetic field lines are horizontal or parallel to the Earth's surface. Now, if you have a closer look at the diagram, I told you the poles are the points where the magnetic field lines are perpendicular to the Earth's surface, or they are vertical. As you go closer to the magnetic equator and as you go far away from the magnetic poles, you see the angle at which they cut the Earth's surface keeps on reducing, keeps on getting lesser and lesser. At the pole, they cut the Earth's surface at 90-degree angle. Now, as you proceed away from the pole, you can see from the diagram, as I'm showing with the laser pointer, with the observer going away from the pole, you can see that the angle at which they cut the Earth's surface keeps on becoming lesser and lesser. So it was 90 at the south pole. You go away from the pole, the angle keeps on becoming lesser, maybe 85 here, 80, 70, 60, 40, and so on. Now, when you reach at the magnetic equator, if you look at the diagram carefully, you will see that the magnetic field lines are parallel to the Earth's surface. Being parallel to the Earth's surface means they are perfectly horizontal, neither coming upwards nor going downwards. They are perfectly horizontal, parallel to the Earth's surface. Similarly, on the other side, if you see, on the other side, the full magnetic field lines are not shown. They have only shown a small portion close to the Earth's surface indicated by an arrow. You can see the angle which the magnetic field line was making at the south pole was 90-degree. You go away from the pole, angle reduces 80, 70, 60, 40, 30, 20, 10, and eventually at this point, when you come at the magnetic equator, you see the magnetic field line is perfectly horizontal or is running parallel to the Earth surface. Again, from the magnetic equator, if you proceed towards the North Pole, magnetic North Pole, you will see the angle will start to increase again. Slowly it becomes 10, 20, 30, 40, 50, 60, and eventually when you reach at the pole, it becomes 90-degree again. So going further, let me show you the instrument with which we observe or find out or measure this dip angle on the surface of Earth at different locations. The instrument which you see here in the diagram on the right side of the screen, this instrument is called as a dip needle. So dip at any place can be observed using this instrument. Now, right now you can see this instrument is having a magnetic needle, having its red end and the blue end, and you can see there is a scale given which measures the dip angle. And right now you can see the dip angle is about 64 degrees, 10, 20, 30, 40, 50. It's about 64 degrees dip at this particular place.
Sir,
Now,
sir, dip is the angle.
this instrument is showing. You how this dip is taken practically. Let me see. I think I have a video. I'll show you. Now, moving further, the magnetic field of the Earth at any particular place is broken down into two components. As you can see in this particular diagram, this slanting line represents the Earth's magnetic field, which is shown as total field intensity, the total force of the Earth's magnetic field. And this angle which you see here, the angle which the magnetic field line makes with the horizontal is known as the dip angle. And this total magnetic field intensity is broken down into two components, the horizontal component and the vertical component. The horizontal component of the total force or the Earth's magnetic field is known as H or HF, horizontal force. Now this H or HF is what makes the compass point towards the magnetic pole, or this H or HF is responsible as a directive force which gives the directive force to our compass. Horizontal force or H giving directive property to our magnetic compass is maximum at the equator, as at the equator the magnetic field lines are perfectly horizontal, and this keeps on reducing as the latitude increases, becoming nil at the magnetic poles, because at the magnetic pole the magnetic field lines are perfectly vertical. They don't have any horizontal component at all. Therefore, the directive property of a magnetic compass is highest at the equator and nil at the poles. This is exactly the reason why the magnetic compass starts to lose its directive force as the vessel goes in higher latitude. Up above about 70 degrees north or south latitudes, the magnetic compass becomes unreliable and loses a substantial amount of its directive force. So is that clear? Now let's move into the ship's magnetism. We have already discussed about the Earth's magnetism. Earth's magnetism is what affects our magnetic compass and provides the directive force to the compass. Now ship's magnetism is another force which is very much present at the compass location and it affects our compass. So we are going to analyze what type of magnetism is present in the ship and how does that magnetism of the ship affects the compass in a positive way or in a negative way, and eventually in the end we are going to see how do we counteract or compensate the effects of the ship's magnetism on our magnetic compass. So let's go into these concepts one by one. Now in the olden days the ships were made of wood. Wood was a non-magnetic material and would not have any magnetism of its own. On such a ship, the only force which affects the magnetic compass is the Earth's magnetism, and the compass would point in the direction of the magnetic poles. Once we identify the magnetic, but nowadays ships are being built of steel, which is a ferromagnetic material. Steel or mild steel or iron is a ferromagnetic material and it has the capability to acquire magnetism. We have seen in the previous slides that two types of magnetism can be generated in ferromagnetic substances. One is permanent magnetism, which was generated by bringing it in contact with a permanent magnet in a specific way. And the second was induced magnetism, which is generated when any ferromagnetic material comes under the effect of a magnetic field. So this mild steel, being a ferromagnetic material, can acquire magnetism of its own, and as we have already discussed, the acquired magnetism by the ship, by the steel of which the ship is made, could be either induced magnetism or it could be permanent magnetism. So these are the two types of magnetism which could be present in the ship structure. Now, based on what type of magnetism is acquired by a particular structure or part of the ship, it is divided into two types. All the structures are divided into two categories. The first category is known as soft iron structures, and the second category is known as hard iron structures. Let us see them one by one. Induced magnetism of the ship is acquired by those parts of the ship or steel structures which instantly and easily get magnetized when placed in a magnetic field. Also, they immediately lose their magnetism as soon as the magnetic field is removed. These type of materials or structures are termed as soft iron structures. Now moving on to the hard iron structures. Permanent magnetism of the ship is acquired by those parts of the ship or steel structures which offer substantial resistance to magnetic changes. These materials do not get magnetized easily, but once magnetized, they retain their magnetism permanently. Now, these kind of structures or these type of materials are termed as hard iron structures. So basically the ship is divided into these two kinds of structure, the soft iron and hard iron structures. Soft iron structures gain or acquire magnetism very easily, and that acquired magnetism is induced magnetism. It is temporary in nature. As soon as the inducing field or the magnetic field which was responsible for the magnetism is removed, the structures lose their magnetism instantly. Whereas on the other hand, the hard iron structures, they do not acquire magnetism easily. Just the presence of magnetic field is not sufficient to acquire magnetism in those structures. But if they get magnetized, then the magnetism remains there permanently. They do not lose their magnetism easily. Now, one more thing to understand before we proceed ahead. It should be very much clear in your mind that these hard and soft words which we have used in the definitions, hard iron structures and soft iron structures, they are basically denoting the two different types of structures or material having different magnetic properties. They relate to their magnetic properties or magnetic behavior. And these materials are not literally hard or soft to touch. Iron, so they are equally hard or soft to touch. It is not that a soft iron structure is pretty soft to touch. No, it is not that way. Do not take the meaning of the words literally. They are just denoting their magnetic properties or magnetic behavior. So into the hard iron and soft iron. Although no structure on the ship can be categorized as entirely or 100% a hard iron structure or a soft iron structures, because any structure on board a ship will possess both the properties in varying degrees. Some part of it will acquire magnetism very easily and lose it equally easily, and some part of the structure will acquire magnetism very slowly, and once acquired it will not leave. So if every structure has both these properties in it, how do we classify them as hard iron and soft iron? Now, these are generally classified on the basis of which out of the two magnetic behavior is predominant in that structure. Let us say we have a particular structure. Let us say we have a mast. Now, in that mast, we analyze and find out that 70% of it has soft iron magnetic properties, and 30% acquires or has the hard iron magnetic properties. So, since predominantly most part of it is a soft iron magnetic behavior part, we will term the mast as a soft iron structure. The ship structures, which are generally prefabricated, means they are made in the factory or made in the yard and fitted on board in situation. Uh, these structures could be the transverse beams, the fore and aft longitudinals, the vertical stiffeners, the mast, the funnel. All these kind of structures, if you see a ship being built in the yard, you will see that all these structures, the beams, the longitudinal, vertical stiffener, mast and funnels, they are basically prefabricated in the yard. They are picked up by a crane, brought to the place where the ship is being constructed, and they are held in place and they are welded there. So these kind of material which are prefabricated predominantly exhibit soft iron magnetic behavior. On the other hand, the ship structures which are extensively worked upon. By worked upon, we mean when the ship is being built, there's a lot of welding or heating or hammering, bending, grinding, cutting. These kind of processes are being made or carried out on those structures. These structures could be the ship's hull, they could be the bulkheads, they could be the decks. Now, these kind of structures predominantly exhibit hard iron magnetic behavior. Go ahead. Okay, let's proceed ahead. Now we are going further into the soft iron and hard iron structures, because this is a very important concept to understand the working as well as the correction of the magnetic compass. The soft iron structures which are present on board, they can be classified into two different categories. These are the vertical soft iron, which has a vertical orientation. It could be the vertical stiffeners. The vertical stiffeners are welded onto the bulkheads, so they have a vertical orientation. Or you could have the masts, forward mast, any cranes, the crane houses, the aft mast, and you have the funnel. All these structures have a vertical orientation on board. The second type of soft iron structures could be horizontal soft iron structures. Now, horizontal soft iron structures could be the fore and aft longitudinals. It could be the athwart ship beams. Both the longitudinals as well as the beams are welded on top of the decks or top of the keel plate or at the bottom of the, you can say, the top deck of the tanks. So they have a horizontal orientation. So these are the two different categories into which the soft iron is divided. In short, the vertical soft iron is also known as VSI, and the horizontal soft iron is known as HSI. Now, if you consider a horizontal soft iron, any doubts up to here, beta?
सर ये सब याद रख.
Okay. As I told you, a horizontal soft iron could be a fore and aft longitudinal or a athwart ship beam. The horizontal soft iron structures on board, are magnetized by the horizontal component of the Earth's magnetic field known as H or HF. Now, when we discussed the magnetic field of the Earth, in that we discussed that at any particular place on the Earth's surface, the total magnetic field intensity represented by this slanting vector can be divided into two components. The horizontal component known as H or HF and the vertical component known as Z. Now, why have we divided them into components? So that we can understand the effect of Earth's magnetism easily onto the ship structure and onto the compass. Now, obviously, if you have a horizontal soft iron structure on board, it will be magnetized by the horizontal component of the Earth's magnetic field, that is H or HF. Now, how is it affected? Now, a blue pole is acquired where the lines of force enter the material, and the red pole is acquired where they leave the material. Now we have seen this that every magnet has its two poles, the blue and the red pole, and we have seen red pole is the one from where the lines of force come out, and blue pole is the one where the lines of force enter into the magnet. So same thing applies here. Let's assume we have a ship which is on a northerly course, 000 course. The ship is at the equator. Now, if you visualize a ship on equator on a heading of 000, you will see that the magnetic lines of force at the equator, they are also parallel to the Earth's surface. They are also horizontal, and they will be entering from the stern of the ship, and they will be leaving from the bow of the ship. Now, if we have a fore and aft longitudinal, the magnetic lines of force will be entering into that end of longitudinal which is toward the stern. And since the lines are entering there, it will have a blue pole at that particular location. Going to the forward end of the fore and aft longitudinal, the lines of force will be coming out from the forward end. So the forward end of the longitudinal will acquire a red polarity. So this is the meaning of the second sentence. A blue pole is acquired where the lines of force enter the material, and a red pole is acquired where they leave the material. Now the strength of induced magnetism generated in a longitudinal is a horizontal soft iron structure. So when it is exposed to the magnetic field of the Earth, it acquires magnetism. But the strength of the induced magnetism depends on the heading of the ship. Let's understand this by taking this example. Know that the H component, the horizontal component of the Earth's magnetic field, always acts northwards. So therefore, the horizontal soft iron structures will receive maximum induction if they lie in the north-south direction, and they will receive zero induction if they lie in the east-west direction. You remember when we discussed about the induced magnetism, I told you that the strength of the induced magnetism depends upon the orientation of the soft iron. If the soft iron structure is oriented or aligned in the direction of the magnetic field, maximum induction would occur. And if it is misaligned, that means it has a orientation perpendicular to the direction in which the field lines are going, it will have minimum or negligible induction. So taking this example, we had a vessel heading in the northerly direction. So a vessel which is heading north, the fore and aft longitudinals, which will also be heading in the lying in the north-south direction, will receive maximum induction from the magnetic field of the Earth. The Earth's magnetic field also is in the north-south orientation. So they are perfectly aligned with the magnetic field of the earth, generating maximum induction. So with maximum induction, it will have strong magnetism acquired. And if you now concentrate on the outward ship beams, our vessel is heading in a northerly direction. So the fore and aft longitudinals were perfectly aligned with the magnetic field, but the outward ship beams on that ship will be oriented in a east-west orientation. Now the magnetic field of the earth is going in a north-south direction. The outward ship beam oriented in a east-west direction. So they are at right angles to each other. So totally misaligned with the magnetic field of the earth. So this tells us that there will be zero or negligible induction on the outward ship beams with the ship lying in the northerly heading. So a ship is on the northerly heading, the fore and aft longitudinals will have maximum induction and the outward ship beams will have negligible or zero induction. So beta, were you able to understand this one up to here?
So my
From this, we are able to understand that the magnetism generated in the horizontal soft iron depends on the heading of the ship. We have seen this ship heading in the northerly direction. There was maximum induction in the fore and aft longitudinal, and there was zero induction in the outward ship beams. You can imagine it in this way now. Let us assume that this particular ship, which was heading in a northerly direction, now changes its heading and alters its course, and now it is heading in the east-west direction. If the ship is heading in the east-west direction, you can now see that the fore and aft longitudinal is also lying in the east-west orientation, and it has become perpendicular to the magnetic field of the earth, which is lying or running in the north-south direction. So when the ship alters course to 090 and is moving on a easterly track, the fore and aft longitudinals are going to lose their induction. There will be no magnetism or negligible magnetic field acquired or generated or induced magnetism generated on the fore and aft longitudinal. Now on the other hand, the outward ship beam in this condition, with the ship heading east, the outward ship beam are now lying in the north-south orientation. The Earth's magnetic field is also in the north-south orientation, so they are perfectly aligned with each other, generating maximum possible induction on the outward ship beams. Thus, the magnetism generated in HSI depends on the heading of the ship. Because as the heading of the ship changes, the orientation of the HSI with respect to the magnetic field of the earth also keeps on changing. The induced magnetism generated in a vertical soft iron or a horizontal soft iron will also change with the position of the ship. Now you see the basic cause of this magnetism, the induced magnetism in soft iron structure, is the magnetic field of the earth. Now if the ship changes its location, let's assume that the vessel was on the equator and now it has moved toward the pole. Now as soon as the vessel changes its location, the Earth's magnetic field, which is the generating force for inducing the magnetism, also changes. So as the vessel changes its position, the magnetic field which is affecting the vessel also changes. The magnetic field at the equator is in a different orientation. Field lines are horizontal. Horizontal component is the strongest. The zero component, the vertical component is the zero component. Now as you move towards the pole, horizontal component keeps on becoming lesser and lesser, and vertical component keeps on becoming stronger. If you go at the pole, you have zero horizontal component and maximum vertical component. So with the magnetism of the earth changing with position, as the ship goes from position A to position B, the induced magnetism in the ship's soft iron structure is also going to change. Now, the induced magnetism in the ship's structure will also change continuously when the vessel is rolling or pitching. Now, when the vessel is rolling or pitching, the fore and aft longitudinal or the outward ship beam or the vertical structures, they are also changing their orientation time and again. With every roll and with every pitch of the ship, the HSI and the VSI are going to change their orientation. And as their orientation changes, the induced magnetism in those structures also changes. Now we are up. Let's now move into the vertical soft iron on the VSI. Just as the HSI, horizontal soft iron on board, was induced by the H or HF component of the Earth's magnetic field, exactly in the same way, the vertical soft iron or VSI on board is magnetized by the vertical component of the Earth's magnetic field. The vertical component is represented by Z. Wherever the magnetic lines of force enter into the structure, it will acquire a blue pole, and wherever the lines of force leave a structure, it will acquire a red pole at that particular location. To give you an example, let's assume we have our ship now at the North Pole. If the ship is at the North Pole, the Earth's vertical component, Z component, is the strongest there. The magnetic field lines at the North Pole are going vertically downwards. So if a ship is standing on the North Pole, you will see that the magnetic lines of force will be going vertically downwards into the Earth's surface. Let's assume or visualize the mast on that particular ship. Let's assume the forward mast. Now with the vertical lines, the lines of force going vertically downwards, they will be entering from the top of the mast. Now this point where the lines of force enter, that is at the top of the mast, it acquires a blue polarity. Wherever the field lines enter into a structure or a magnet, a blue pole is acquired, and these vertical lines of force going downwards will be coming out from the base of the mast. So the bottommost part of the mast or the base of the mast from where the magnetic lines of force are leaving or going out gets red polarity. It acquires red polarity because wherever the lines of force leave or come out from a structure or a magnet, it acquires a red polarity at that location. Now let's assume that this same ship starts moving now. The top of the mast was blue and the bottom of the mast was red. This ship has started traveling now, and this ship now has crossed the equator and gone into southern hemisphere, and it has reached the South Pole. Now the same ship is at the South Pole. We are aware that at the South Pole the magnetic lines of force, they come out from the Earth's surface. Now when they come out of the Earth's surface, they will be entering the mast from the bottom, thus giving it a blue polarity. The bottom of the mast now acquires a blue polarity, and these lines of force will be leaving from top of the mast, giving it a red polarity.
Yes.
So now it means we are now will be discussing about hard iron structure.
Bulkhead, deck.
Go ahead, beta. What are you asking?
So We will be discussing now about hard iron.
That's right, beta. Exactly right. We will be now discussing about the hard iron structures. In this position till the time the construction of the ship is complete. In a yard or in a dock, when you start the shipbuilding, laying down the keel of the ship remains in the same orientation till the time it is ready to be launched for sea trials. So the Earth's magnetic field will keep on affecting the ship in this particular orientation only. So you can see the magnetic field lines are entering from the top deck of the ship and they are leaving out from the keel of the ship. So the hull of the ship lies in one constant direction and is worked upon. When the ship is being constructed, we will be welding the plates, we will be hammering them, bending them, heating them. A high voltage electric current will be passing at the time of welding. So we will be using grinders, cutters, all these instruments on them. So all the ship's plates which are being fitted will be worked upon at the time of shipbuilding. Now during this entire process, which happens over a long period of time, it may take 1 year or it may take 6 months for the ship to be built. So during this long period, the Earth's magnetic field continuously acts on the hull in the same direction or the same orientation. Now, since we are working upon all these metal plates which are being fitted on the ship, and the Earth's magnetic field is acting on it in the same orientation, it generates permanent magnetism in these hard iron structures. So I told you that hard iron structures are those structures which are extensively worked upon at the time of construction of the ship or shipbuilding. Like say for example a keel plate, a deck plate, a bulkhead. Now when you are fitting this, let us assume there is a deck plate, you are fitting this deck plate on the deck of the ship during its construction. Now you will be cutting the plate, making it to size, you will be bending it as required, you will be hammering it, then you will be welding from the seams, then you will be welding a stiffener or a longitudinal on it or a transverse beam on it. So all these things, when they are happening and we are working upon this particular deck plate, the Earth's magnetic field is acting on that deck plate in one particular orientation, and this Earth's magnetic field acting on it during all this jobs or work being done generates a permanent magnetism in these structures. Since lot of working upon is being done, they are hard iron structures, and the Earth's magnetic field generates a permanent magnetism in these hard iron structure. Now, as this is permanent magnetism, once the material acquires it, it will not then change with time or with the position of the ship. The permanent magnetism once acquired remains there in the structure and it will not change with time or when the ship changes its position. Now, since it is permanent magnetism, the poles which are generated, as we have seen, a blue pole is generated where the lines enter the material and a red pole is generated where they leave the material. The poles generated are also permanent. The course or the heading of the ship or the rolling pitching motion of the ship will not have any effect on them. Once these poles are generated, the rolling pitching of the ship, the course of the ship, the heading of the ship, the position of the ship will not have any effect on these poles because these are permanent poles. Now the ship which I showed you in the previous slide, the lines of force were entering on the deck and they were leaving out from the keel. So if there is a bulkhead, let us say you are welding a bulkhead in place, intertank bulkhead, the topmost part of the bulkhead is going to acquire blue polarity, and the bottommost part of the bulkhead is going to acquire red polarity, and these poles will remain permanent always, as they are permanent magnetism. The vessel is going to acquire magnetism both in the horizontal and vertical planes. I will explain this to you with the help of diagrams going further. A blue pole is acquired where the lines enter the material, and a red pole is acquired where the lines of force leave the material. Now, as I told you that this permanent magnetism is acquired both in the horizontal direction and the vertical direction. Now, let's try to understand that by making some diagrams. Let us assume that we have a ship being built at a yard which is on the equator. We have a yard somewhere on the equator and the ship is being built. Two ships are being built there. One of the ships is put in the yard heading in the southerly direction. So right now you see where my laser pointer is. This ship is being built in the yard on a southerly heading. This is how the orientation of the yard is. Now, if it is being built on a southerly heading, you see a red color pole here at the bottom or at the south. This is basically the south pole or the south magnetic pole of the earth. And you see a blue pole at the top or north of the ship. This represents the north magnetic pole of the earth, which has the blue polarity. And these dotted lines which you see, the dotted lines going from red pole to the blue pole, they represent the magnetic field lines of the earth. We are aware that magnetic field lines come out of the red pole, which is the south magnetic pole of the earth. They are all coming out from the red pole, and these lines of force, they re-enter or go into the blue pole or the north magnetic pole of the earth. So that is why you see the arrows are always from red to blue. Now this magnetic field is affecting the ship which is being built, and all these magnetic field lines, they are entering into the ship structure from the bow side, giving it a blue polarity, and they are leaving out from the ship from the stern side, giving it a red polarity. Why the bow is blue in this case? Because wherever the magnetic field lines enter, that is the blue pole. Is the stern red in this place? The stern is red because wherever the lines of force come out, that is the red pole of the magnet. So with the lines of force entering into the bow, it gets a blue polarity, and with the lines of force coming out of the stern, it gets a red polarity. Now, let's assume that there is another ship which is being built in the same yard but in a different dock, and that dock has a northeasterly orientation. So you now concentrate on the ship on the right side. This ship is heading in a northeasterly direction. The south pole of the earth is at the same location, north pole is at the same location. Magnetic lines of force of the earth are moving in the same orientation from south to north. But with the ship heading in the northeasterly direction, now if you look carefully, the magnetic field lines are entering into the ship structure from the starboard quarter side. So you see, starboard quarter is where the lines of force are entering, and that is where a blue pole will be acquired. These lines of force are coming out of the ship structure from the port bow, and that is where a red pole will be acquired. So you compare both these ships now, you see with the change in heading of the ship, the horizontal positioning or location of the poles has also changed. So is this part clear, beta? Any doubts up to here?
No, sir.
Very good, beta. So this was the horizontal positioning of the poles. Let me now show you the vertical positioning also. Go ahead, beta.
Sir, so there will be so many points where there will be blue polarity, not only just one point, sir.
Assume a ship which is built in the northern hemisphere. You see these two ships on the top. This one is built on the northern hemisphere, at some place on the northern hemisphere. This ship also is built in the northern hemisphere. This ship is being built in the yard, somewhere located in the northerly latitudes. Now you see that when the ship is being built, the magnetic lines of force will be coming into the Earth's surface. So they will be entering from the deck of the ship and they will be coming out or leaving out the ship from the keel. So since they are entering into the deck of the ship, it will acquire a blue polarity. And since they are leaving out or coming out from the keel of the ship, it will acquire a red polarity. This is exactly the same situation for which I showed you the diagram in the previous slides also. We saw a ship standing in a yard and the magnetic field lines were going vertically downwards. So they were entering from the deck, giving it a blue polarity, and they are coming out from the keel, giving it a red polarity. So if the ship is built anywhere in the northern hemisphere, it will have a blue polarity deck and a red polarity keel of the ship. Now let's visualize a ship being built somewhere in the southern hemisphere. So this is the ship you see being built in the southern hemisphere. Now in the southern hemisphere, we are aware that the lines of force come out of the Earth's surface. So you see the lines of force coming out of the Earth's surface will enter from the keel of the ship, giving it a blue polarity, and they will come out from the deck of the ship, giving it a red polarity. So any ship which is built in the southern hemisphere will have a blue keel and a red deck. Any ship built in the northern hemisphere will have a red keel and a blue deck. So when you come to know the location where the ship is built and the heading on which the ship is built, you can find out easily what is the vertical and horizontal positioning of the poles. So beta, up to here, let me know any doubts coming to your mind. Depending on the heading of the ship and the hemisphere in which the ship is built, the positioning of the permanent pole could result in any oblique direction. The permanent magnetism vector could be present in a three-dimensional orientation. You can understand it from this particular diagram. We have this particular ship here, and the permanent magnetism is represented by this oblique slanting vector. This vector represents the permanent magnetism of the ship. One of the poles is on the deck towards the port quarter, and other pole is at the keel towards the starboard bow. So this vector represents the permanent magnetism of the ship. Now to counter this permanent magnetism, to rectify it, to correct it, this permanent magnetism in any oblique direction is split up into three mutually or split this oblique vector in three mutually perpendicular directions. One of the component is split component the fore and aft direction. This is known as the fore and aft component of the ship's permanent magnetism, and it is represented by alphabet P, Papa. Then you see this second vector, this vector, this is the second component. This is the authorship component of the ship's permanent magnetism, and it is represented by Q, Quebec. And the third component is the vertical component. You can see this particular arrow shows the vertical component of the ship's magnetism. This is known as the vertical component, also called as the healing component, represented by alphabet R Romeo. Now, why are we breaking it up into three vectors like these? This is because it is very difficult to counter the permanent magnetism in a oblique direction in any 3D orientation. But when you split it up in three mutually perpendicular directions, that is fore and aft, authwardship, and vertical, it becomes easy for us to counter all these three components one by one. When we do the compass correction, we will see how this fore and aft component is corrected. Then we will see how this authwardship component is corrected, and we will also see how the vertical component is corrected.
So I'm not understanding where is this outward shift Q. Okay, I got it. Got it.
Yeah, it's a 3D kind of diagram, beta. It is basically coming out of the screen towards you.
Yes, understood, sir.
Yeah, okay.
Excuse me, sir.
Go ahead, beta.
Sir, what is mean by this?
To the concept of compass work. Correcting a compass is also known as compass work. So what is the concept behind it? Permanent magnetism and induced magnetism both cause deviation of the magnetic compass. Now, as I told you, if our magnetic compass is affected solely by the magnetic field of Earth, it will give us precisely the variation. Variation can be easily picked up from the chart and applied. And once applied, it gives you true directions. But if you have the magnetism of the ship, permanent or induced, will disturb and distance known as. The permanent magnetism can be easily understood by considering its three components or by breaking it up into three components. That is the P component, which is in the fore and aft direction, this one. Then the Q component, which is in the outwardship direction, and vertical. So understand these three components of the permanent magnetism, we can cancel it or counteract it one by one. The induced magnetism can also be generated in three different directions. It can be broken up into three different directions. You have the induced magnetism generated in the fore and aft direction. In fore and aft horizontal soft iron, that could be a fore and aft longitudinal. This is one orientation in which induced magnetism can be generated. Induced magnetism can also be generated in the outwardship direction. In outwardship soft iron, which could be the transfers of the outwardship beams, and it can be generated in the vertical direction, which happens in vertical soft are masts, cranes, or funnels, or vertical stiffeners. Now, each of these components has to be treated separately. You see, permanent magnetism, three component, fore and aft component, authorship component, vertical component, in fore and aft horizontal fore and aft structures, induced magnetism in horizontal authorship structures, and induced magnetism in vertical structures. They all have to be treated separately. There are six total components of the ship's magnetism, which affect our compass. They need to be treated separately as the deviations which they generate
वाईफाई बंद कर दियो के यार
ना यार वाईफाई का करना भी कोई ना कोई which should be able to judge this and provide a correction in the fore and aft direction of the same amount. Now, when the ship goes to a easterly course, the fore and aft longitudinal loses its entire magnetism. Induced magnetism is lost. So our corrector should be such that it senses that the fore and aft longitudinal has now become powerless, and the correction which it was providing is also brought to zero. So we need a correction mechanism for each of these components, treating them separately, and it should be such a mechanism which keeps on changing its correction depending upon the change in the permanent or induced magnetism of the ship. This is what we call as component, the compass work. Now, for treating these components, the deviation of the compass is divided into 5 different parts which we know as coefficients. So as I told you, we need to tackle these components separately one by one. So therefore, how do we tackle them differently? By dividing the deviation of the ship into 5 different parts. These parts are known as coefficients. Now, what are these coefficients? These coefficients are named as A, B, C, D, and E. The first 5 alphabets, A, B, C, D, and E. This is how the coefficients are named. Now, it must be clearly understood that these coefficients A, B, C, D, E are the deviations generated and not the forces causing the deviations. The forces which are causing the deviations are permanent magnetism of the ship, broken down into 3 components: fore and aft P, outward ship Q, vertical R, and the induced magnetism of the ship in HSI, horizontal soft iron, fore and aft, in outward ship HSI, and in vertical soft iron. These are the forces which are generating the deviations. What we have now done is, let us say, to give you an example, the ship is on a particular heading and the deviation is 10 degrees east. Now this 10 degree east comprises of all these 5 coefficients in it. The coefficient A could be contributing 2 degrees, coefficient B could be contributing 5 degrees, coefficient C could be contributing 0 degrees, and so on. When the ship changes its heading, the contribution of all the coefficients may also change. Okay. Now, how are these coefficients made? This is very, very important to understand. How are these coefficients specified or made? These coefficients are broken up as per the forces causing them. So depending upon what force is causing it, we have divided it into categories. So this is something which is new for you. You have not studied this in the second mates level. So once you understand this concept of coefficients, then the entire compass correction will be very easy to handle. Let us say, for example, as I told you, a ship is having 10 degree east deviation at a particular heading. Now, out of which, let us say, 2 degrees of deviation is being caused by the magnetism of the ship in the fore and aft direction. The magnetism of the ship in the fore and aft direction. It may have a permanent component, which is P component. P component is the component of the permanent magnetic field of the ship in the fore and aft orientation. And it may also have some induced magnetism. Induced magnetism, let us say ship is heading in a northerly direction, and there is a induced magnetism in the fore and aft longitudinal, and it may generate this particular deviation. So this deviation being generated by the magnetic field in the fore and aft orientation can be categorized as coefficient A. I've just given you an example how the deviation is broken up into 5 parts. So basis its causing factors, the deviations are broken up into different parts. If we know all the coefficients, the total deviation can be calculated on any particular heading of the ship. If we know the coefficients of a particular compass, let's say you go on a ship and I tell you that these are the 5 coefficients. Coefficient A is this much, coefficient B is this much, coefficient C is this much, and so on. Once I tell you all the coefficients, it is very easy for us to calculate the total deviation generated. Now, how can it be done? We have a very simple formula for finding the deviation from the coefficients. The formula is deviation is equal to coefficient A plus B sine cos plus C cos. Our first coefficient, that is coefficient A. Coefficient A is a deviation which remains constant in name as well as magnitude on all the headings and is further divided into 2 parts. These 2 parts are number 1 real A and number 2 apparent A. Now, if you remember the formula which I had shown you, the formula for deviation, in that formula we saw that this coefficient A is not connected with the ship's course in any way. Indirectly, that means that whatever be the course of the ship or whatever be the heading of the ship, the value of coefficient A is not going to change. And you see exactly that is what the definition also tells us. Coefficient A is a deviation which remains constant in name as well as magnitude on all the headings. The vessel can continue to change its heading and the deviation which is generated because of coefficient A does not change at all. It has 2 components and it can be divided into these 2 components. One is called as real A, another is called as apparent A. What is this real A part of the coefficient A? It is a constant deviation on all the headings caused by induced magnetism in unsymmetrical pairs of horizontal soft iron. I will explain this to you in detail by showing this kind of structure in the diagram. So for now, just understand it is caused by induced magnetism in unsymmetrical pairs of HSI, horizontal soft iron. So the cause of real A is the horizontal soft iron on board. The second part, which is called as apparent A. Apparent A is a constant deviation on all the headings, which is caused by factors other than the magnetic field. So up to here clear beta? Any doubts? Bolo beta. Let me now show you the kind of structures which may generate coefficient A on a particular ship. Now we have seen that coefficient A is generated because of unsymmetrical pairs of horizontal soft iron. Now horizontal soft iron HSI can be present in 2 orientation. We can have a fore and aft horizontal soft iron, something like this one. This is horizontal soft iron in the fore and aft direction, and we can also have horizontal soft iron in the athwart ship orientation. You now see another horizontal soft iron which has a athwart ship orientation. So the first thing to note is that coefficient A require a pair. Pair means there should be a combination of fore and aft as well as athwart ship horizontal soft iron. The second thing which is required is that these horizontal soft iron should be unsymmetrical. Now what do we mean by unsymmetrical? If you look closely, the fore and aft HSI which we have is present only forward of the compass location. The circle which you see in the middle of the ship is representing the compass, the binnacle, and the HSI in the fore and aft orientation is only present forward of the compass and it is not there aft of the compass. This kind of a HSI is known as unsymmetrical HSI. Likewise, this athwart ship HSI which you see is present only on the port side of the compass and it is not present on the starboard side of the compass. So both these HSI are unsymmetrical. That means they are present only on one side of the compass and there is a pair present, means both fore and aft and athwart ship HSI are present. This kind of a combination, if it is present on a ship, will generate coefficient A. Now, usually we do not see any kind of these structures on a normal merchant vessel. You will always have symmetrical HSI. So that is exactly the reason why coefficient A is absent on most of the normal merchant vessels. Such a configuration of horizontal soft iron on board a ship, so these kind of structures are present. How do they result into a real A coefficient? Or in other words, how do they generate a deviation which is constant irrespective of the heading of the ship? Whichever heading the ship goes, the deviation generated by these structures remains constant and does not change. So let us try to understand it. Now this is understood by making a deviation diagram. For every coefficient, we will be making a deviation diagram like the one you see on the screen now. We have the ship on different headings: north, northeast, easterly, southeast, south, southwest, westerly, and northwesterly. So cardinal and intercardinal heading, the ship is shown on these 8 headings. And in each of these headings, we are going to analyze that how do these horizontal soft iron structures, it is an unsymmetrical pair of horizontal soft iron structures, they generate the deviation which does not change. So we will first try to understand how do these structures affect our ship, and second we will try to see that how does this effect remain same irrespective of the heading of the ship. So let's try to concentrate our attention with the ship on the northerly heading. The ship is on a north heading. You can follow the laser pointer. This is the diagram which we are going to see or understand in detail. Now the ship is on a northerly heading. We have these 2 soft iron structures. One a athwart ship beam which is only present on the port side of the compass, and we have a fore and aft longitudinal which is present on the starboard side only forward of the compass. It is not present aft of the compass. So we have combination number 1 which we saw in the previous slide, a unsymmetrical pair of horizontal soft iron structures. You see this big blue color rectangle on top. This represents the north magnetic pole of the earth. We are aware that the north magnetic pole of the earth has blue polarity. And you see this red color rectangle at the bottom. This represents the south magnetic pole of the earth, and we are aware the south magnetic pole has a red polarity. Now we know that the magnetic lines of force, they come out of the red pole and they go into the north pole. So the magnetic lines of force coming out of the red pole going into the blue pole. So in this particular diagram, you will see that the magnetic lines of force are going vertically upwards from the red pole to the blue pole of the earth, going vertically upwards like this. Now with the magnetic field of the earth going vertically upwards, it will affect both these structures. It will affect the fore and aft longitudinal also, and it is going to affect the authorship beam also. Now first thing to understand is that these are soft iron structures, so they do not have any permanent magnetism. There is no permanent magnetism in these structures. But being soft iron structures, they can get induced by the magnetism or magnetic field of the earth. Now the magnetic field lines are going vertically upwards. If you concentrate your attention to the authorship beam, this authorship beam is not oriented or aligned in the direction of the magnetic field. It is at right angles to the magnetic field of the earth. Used magnetism, I told you that there is minimum induction or zero induction, negligible induction when the soft iron structure is misaligned with the inducing field. The inducing field in this direction is in the north-south orientation, and this authorship beam is in the east-west orientation. The vessel is heading north, so the beam is in east-west orientation. So this beam is at right angles to the inducing field or the magnetic field of the earth. Now being at right angles, no induction happens. No magnetic field induction happens here, and the authorship beam does not acquire any magnetism. There are no poles which are generated. Let's now concentrate our attention to the fore and aft longitudinal. The fore and aft longitudinal, if you look carefully, is aligned exactly in the same direction in which the Earth's magnetic field lies. The magnetic field lines are in the north-south orientation. The fore and aft longitudinal is also exactly in the north-south orientation. So the fore and aft longitudinal is perfectly aligned with the magnetic field. And this tells us that there will be maximum induction in the fore and aft longitudinal. Maximum induction. So we know the fore and aft longitudinal having maximum induction will become a strong magnet now. Let us now understand the direction of the poles which are generated. We see the magnetic field lines are coming out from the red pole of the earth and going into the blue pole. So this tells us that these magnetic field lines will be entering into the aft end of the longitudinal. If they are entering into the aft end of the longitudinal, wherever the lines of force enter, that end gets a blue polarity. Wherever the magnetic lines of force are entering, that end of the magnet has a blue polarity. So that's why you see the aft end of the fore and aft longitudinal has a blue magnetic pole. And these lines of force going from south to north will be coming out from the forward end of the longitudinal, the forward end. Since they are coming out of the forward end of the longitudinal, you will see that the forward end of the longitudinal acquires red polarity. So this is the reason why you see in the diagram the aft end of the longitudinal has blue polarity and the forward end of the longitudinal has red polarity. So we now understand the different poles generated on the fore and aft longitudinal. The induction or induced magnetism of the horizontal soft iron structures by the Earth's magnetism. Let's now try to see that at different headings, what is the deviation which is generated because of this induced magnetism. So as you can see in the diagram, at every heading, they indicate to us that it is a easterly deviation. You see north heading, northeast, easterly, southeasterly, southerly. On all the headings, they are denoting that the vessel has a easterly deviation. And in the definition of coefficient A, we have seen that it generates a constant deviation irrespective of the heading. So we will try to see now how does this deviation remain constant over all the headings. Let's first of all try to understand how this easterly deviation is generated with the ship on northerly heading. So what I'm going to do is I'm going to zoom in into this diagram with the ship heading north. We are aware that we have a fore and aft longitudinal and a outward ship beam. There is no induction on the beam right now because it is at right angles to the Earth's field, and there is maximum induction in the fore and aft longitudinal. So let's now try to zoom in into this. So here on the left side, you see a zoomed in diagram with the ship heading north. Let's first make the magnetic compass on this ship. Now we know the magnetic compass is basically a magnet, and the end which points towards the north is the red end of that magnet. So let's show our magnetic compass. You can see it here. The north end of the magnetic compass is having a red polarity. You see the red color, and the south end is having a blue polarity. So this arrow which you see in the zoomed in diagram of the ship now represents the magnetic compass. And we have a longitudinal which is to the starboard side of the compass, and it is forward of the compass location. It is not present aft of the compass location. So you can see this longitudinal in the zoomed in diagram now, and it is to the starboard side of the compass and is extending to forward of the compass. Now we have already seen that this particular end, the aft end of the longitudinal, acquires a blue pole, and the forward end of the longitudinal acquires a red pole. This is a soft iron structures, and these poles are acquired as induced magnetism, which are generated by the magnetic field of the earth. Now whenever we bring a magnet close to our compass, every magnet has two poles, a red and a blue pole. We cannot have a single pole in a magnet anywhere. Even if you break up a magnet, the broken ends immediately acquire the polarity. You cannot have a single pole at any point. Now whenever you bring a magnet close to the compass, it has both the poles, the red as well as the blue. Now which of the poles is going to affect the compass? Always, in all the conditions, that poles affect the compass which is closer to it. Because as you go far away from the pole, the magnetic field or its strength or its power reduces. It is inversely proportional to square of the distance. Means if you increase the distance by twice, the magnetism or magnetic field strength of the pole goes down by 1/4. So whenever you bring a magnet close to the compass, that particular pole which is closer with respect to the other has its effect on the compass. Now in this particular case, the longitudinal is having two ends. One of the ends is very close to the compass, which is having a blue polarity, whereas the other end, for clarity I have exaggerated a bit and taken it out of the ship's hull. So the other end of the longitudinal is close to the bow of the ship, which is much farther away as compared to the blue pole. So in this case, blue pole is the one which is going to have its effect on our magnetic compass. Now, how does this blue pole affect our compass? The effect of this blue pole onto the red end, that is the north end of the compass, will be attraction. Because we are aware that opposite poles of a magnet attract each other. So this blue pole of the fore and aft longitudinal is going to attract the north end of our magnetic compass or magnetic needle. So when it attracts the north end towards it, the compass is going to deviate to the right side. Looking at the diagram, it is going to deviate to the right side, and that is easterly side. With the vessel heading north, the right side is easterly direction, so a easterly deviation is generated. Also, you can see this blue end is also going to interact with the south end of the compass. The south end of the compass also has a blue polarity. Now we know that the same poles of the magnet repel each other. So this blue pole of the longitudinal is going to repel the blue pole or the south end of our magnetic compass, again generating easterly deviation. The compass needle is going to swing clockwise, which is easterly deviation. So that is why you see they have mentioned here as easterly deviation. Try to understand the deviation generated on 090 heading. We take the ship on 090 heading and we try to understand what is the deviation generated. Now you see when the ship is heading 090, the fore and aft longitudinal is heading in the east-west direction and it is now perpendicular to the Earth's magnetic field. Earth's magnetic field is in the north-south orientation. With the longitudinal in the east-west orientation, it is at right angles to the Earth's field and it is totally misaligned with the inducing field. That is why no induction on the fore and aft longitudinal. On the other hand, the outward ship beam is now perfectly aligned with the magnetic field of the Earth. The Earth's magnetic field is in the north-south orientation. The outward ship beam is also in the north-south orientation. Perfectly aligned, it generates maximum induction. So you see onto the starboard end of the beam, a blue pole is generated because this is where the lines of force are entering. The lines of force come out from the red pole of the Earth and they go into the blue pole of the Earth. So the starboard end of the outward ship beam acquires a blue polarity and the port end of the outward ship beam acquires a red polarity. Now to see its effect, let us now zoom into this particular diagram of the ship. We can zoom in and see the effect in detail. You can see the zoomed in diagram on the left side now. The vessel is heading in the easterly direction. The fore and aft longitudinal does not have any magnetism, so that's why it is not shown in this diagram. There are no poles generated there. The outward ship beam is present forward of the compass only on the port side. You see it is unsymmetrical, so it is not present on the starboard side of the compass, it is only present on the port side of the compass. Being unsymmetrical was a requirement of generating real a deviation. Now we have seen the south end of the outward ship beam acquires a blue polarity. This is where the lines of force are entering. And the north end of the outward ship beam acquires a red polarity. Now the north end of the beam is close to the ship side and is far away from the compass, whereas the south end of the outward ship beam is very close to the compass location. It's very close to the compass location. So blue end is what affects our compass. The ship is heading in the easterly direction. Compass always points in the north-south direction. So compass is pointing in this particular direction only. And we have a blue pole to the east of the compass. This blue pole attracts the red end or the north end of our compass needle, and the blue pole repels the blue end of the compass needle or the south end of the compass needle, again making the needle swing clockwise, generating a easterly deviation. So you can see again a easterly deviation is generated. So whether the ship is on north heading or the ship is on easterly heading, in both the cases, easterly deviation is generated. With the ship heading in the northeasterly direction. So with the ship heading in the northeasterly direction, how does the deviation behave? Let's zoom into this diagram of the ship. So on the left side, you see the zoomed in diagram of the ship. Compass as usual placed in the center line. Irrespective of what is the direction in which the ship is heading, the compass needle is always going to point north and south. The north end will be the red end of the compass and the south end will be the blue end of the compass. Now we have a longitudinal, 4.5 longitudinal to the starboard of the compass. So you can see on the starboard side we have a 4.5 longitudinal which is only forward of the compass. It is not there aft of the compass. We also have a athwartship beam. The athwartship beam is forward of the compass and only to the port side. You can see the athwartship beam is only to the port side of the compass. It is not present on the starboard side. Now I have taken the far ends of the longitudinal and the beam out of the ship's hull just to make the picture a little more clear and easy for understanding. Now in this case you see the Earth's magnetic field coming from south to north is going to induce both these structures because both of these structures are now at a 45-degree angle to the Earth's magnetic field. They are neither fully aligned nor misaligned. They are partially aligned with the magnetic field of the Earth. So there will be partial induction on both these structures. That is the longitudinal as well as the beam. Partial induction on both of them. So the poles generated will have partial power. And now you look carefully. The blue pole is generated in the longitudinal as well as the beam, and this is the pole which is closer to our compass. The red poles generated are far away from the compass. So blue poles are the one which are going to affect our compass. Now the blue pole of the athwartship beam is closer to the red end or the north end of the compass, and it is going to attract the compass towards it. Whereas the blue pole in the longitudinal is close to the south end of the compass, which is again blue, and both being the same polarity, they are going to repel each other. And you will see, even though there are two poles, they are both trying to swing the compass in the clockwise direction again. So you see, the compass has to swing clockwise again, generating easterly deviation. Now one doubt may arise that since there are two blue poles now, the deviation generated will be more powerful, but that is not the case. Reason being, even though two poles are generated, but both of them have partial power. Why the power is partial? Why their strength is partial? Because they are not perfectly aligned with the magnetic field of the Earth. Both the longitudinal and the athwartship beam are partially aligned, making these poles partially powerful. So when both these poles add up, they generate the same easterly deviation which was generated on 000 heading and 090 heading. So you can see, irrespective of the heading on which the ship is, the deviation generated remains the same. So I hope it is clear now, beta.
Sir, for this northwest
Sir,
direction, HSI.
Yeah. Correction of real A. How do we correct this coefficient? The correction of real A is generally not attempted, not done. The reason for it is, number one, It is very rare on a normal seagoing merchant ship that a coefficient A will exist, because these kind of soft iron structures are not present on the ship. Whatever soft iron structures are present, they are symmetrical about the compass location. Even when it is present in some ship, it is likely to be very, very small. So this is the reason why we do not attempt the correction of real A. What is done then? Since the deviation generated is constant on all the headings, it can be applied as an index error. So you will see that on a ship where real A is present, the real A value will be mentioned separately in the deviation card. Like, let us say, for example, the deviation card will tell you that the real A correction or index error correction is 1 degree east. So whatever deviation you obtain from the curve, you add 1 degree east to that deviation and it will give you the resultant deviation. So deviation being constant on all the headings, is it applied as a index error, and the real A is not generally corrected. Now the second component of coefficient A, which is known as apparent A, is basically the constant deviation on all headings caused by factors other than the magnetic field. So any reason, any cause other than the magnetic field which leads to a constant error on all the headings will come under apparent A. There can be numerous reasons for generation of apparent A. Some of the examples, some possibilities which could lead to this kind of an error. You can have the magnetic needles of the card not parallel to 180-degree direction of the card. Now this is a manufacturing defect. You can visualize a card is being printed. The magnets are to be fitted exactly in the 000180 direction. But if during the construction of the card, the magnets are fitted slightly at an angle, let us say 002 and 182 direction, so there will always be a slight error which the compass will show. This has got nothing to do with magnetism, so this falls under apparent A. That's a manufacturing defect in the card. Sometimes we see there is a lubber line which is fitted on the repeater. If the lubber line is not parallel to the ship's fore and aft line, so whenever you read that lubber line to get the heading of the ship, there will be a constant error. This has got nothing to do with magnetism, and it's also a manufacturing defect, so it falls under apparent A. Other reason could be constant error in observing the bearings when the compass is initially adjusted. For example, there could be an index error in the azimuth mirror leading to wrong deviation card. So when that wrong deviation is applied, you will get an error. So that's also a non-magnetic reason. Further reasons could be error in computing the magnetic bearing when the compass was adjusted, rapid swinging of the vessel when observing the bearing for compass adjustment. It is recommended that whenever we are doing the compass adjustment, the vessel should not be swung rapidly. It should be steadied on a particular heading before noting down the deviation. Or are angles worked out wrongly leading to error in the calculated bearing? We usually obtain the compass error by using the azimuth, calculating the azimuth by ABC method. So if the method has been worked out wrongly, it will lead to a wrong deviation being noted down. And if we use that wrong deviation, it will give us wrong bearings or wrong heading of the ship. So there could be many other reasons also. Any reason other than magnetism which leads to a constant error on all the headings falls under the category of apparent A. For the correction purpose, the value of coefficient A can be easily obtained as the mean of deviation on at least 4 equidistant headings. What does that mean? Let us take the ship on a northerly heading and note down the deviation. Let's now take the ship on a easterly heading, note down the deviation. then southerly heading and westerly heading. So all the four cardinal headings, we swing the ship, take it to four cardinal headings, and we note down the deviation on these four headings. Now, once you take a mean of these four deviations, it gives you the value of coefficient A for that particular ship. Practically, this is done using 8 deviations on cardinal and intercardinal headings. Taking this value in 8 deviations gives you more accuracy. So practically we use the deviations on cardinal and intercardinal headings and take a mean. Now you can easily test out this method or try out this method using this formula. This is the same formula which I showed you. Deviation is equal to coefficient A plus B sine cos plus C cos cos plus D sine 2 cos plus E cos 2 cos. So in this formula, if you put the course as 0, 0, 0 and get the result, then second time you put the value as 90, third time you put the value as 180, fourth time you put the value of course as 270. Now once you get the answers and you take a mean, you will see that all the other coefficients B, C, D and E will get cancelled out. The only coefficient which will remain is coefficient A. Now let's move on to the second coefficient, that is coefficient B. The definition says coefficient B is the maximum value of the semicircular deviation which varies as the sign of the compass course. Now in the formula which I gave you, in that particular formula, what is that part which is proportional to or which varies as sine of the compass course? It is the second part of the formula, that is B sine course. Now the maximum value of that deviation is what is coefficient B. So you see this definition has been picked up, or you can easily remember this definition basis the formula. Coefficient B is the maximum value of the semicircular deviation which varies as sine of the compass course. That part of the deviation which varies as sine of the compass course, the maximum possible value what it can have is what is coefficient B. Now, what is the meaning of semicircular deviation? Now we know one circle is 360 degrees. So if a deviation carries the same name over the entire 360 degrees, if it is east and it remains east for the vessel heading on entire 360 degrees, it is called a circular deviation. A deviation which is of one single name for a semicircle, that is 180 degrees, and in the other semicircle, the remaining 180 degrees, it gets a opposite name. It is called as a semicircular deviation. To give you an example, let us say on a particular ship you observe the deviation from heading north to south. It is easterly deviation, and when the ship heads from south to southwest, that is 180, 190, 270 up to 360 in the southwest and northwest quadrant, the deviation is westerly. So you see now for 180 degrees the deviation was east, for the next 180 it has changed to westerly direction. Such a deviation is called as a semicircular deviation. Deviation changes after every 90 degrees. For the first quadrant, the northeast quadrant, the deviation was easterly. For southeasterly quadrant, the deviation becomes westerly. For southwesterly quadrant, it again easterly, and for northwesterly quadrant, it becomes westerly. Means it changes after every 90 degrees. It is known as a quadrantal deviation. So semicircular deviation means that for 180 degrees out of the total 360, it will have one particular name, either east or west, and for the remaining 180 degrees, the name is going to is
There is
the
some disturbance.
horizontal fore and aft component of the ship's magnetic field. Go ahead, beta. Horizontal fore and aft component of the ship's magnetic field is caused or generated by permanent magnetism of the ship as well as induced magnetism of the ship. So the contributing factor for coefficient B are both permanent magnetism as well as induced magnetism. The part of coefficient B generated by permanent magnetism is called permanent B, or in short PB, Papa Bravo, and that part of the coefficient B which is generated by induced magnetism is called induced B, or in short form IB. Let's now see the cause of permanent B on a ship. Now we are aware, concentrate your attention to the diagram, first diagram on the left hand side where the laser pointer is right now. Let's assume that this ship is being built in the yard on a northerly heading. If it is built in a northerly heading, the lines of force will be entering from the stern of the ship and leaving from the bow of the ship, giving the stern a blue polarity and the bow a red polarity. Now, if the ship was built on a southerly heading, then in that case, you will have a blue bow and a red stern. Now, these poles which are generated are permanent poles. So, depending upon whether the ship was built on a northerly heading or a southerly heading, you will have a blue bow or a red bow. Now, when the ship has magnetism in this particular way, it has a blue bow and a red stern. How does this magnetism affect our compass? If you look carefully, this is the permanent magnetism of the ship in the horizontal fore and aft direction. What causes permanent B? So let us see its effect on our magnetic compass. Now this is a diagram which is showing us, this is the deviation diagram for coefficient B. It is showing us a ship which has a blue bow. You see everywhere at the bow we have a blue pole, and this ship is having a red stern. So this tells us that this particular ship was built on a southerly heading. So just now, as we saw in the previous slide, a ship which is built on southerly heading will have a blue bow, the lines of force will be entering there, and a red stern. Now, how does this permanent magnetic field of the ship in the horizontal direction, fore and aft direction, going to affect our compass? Let us see it heading by heading. Now, with the ship heading in the northerly direction, we have a blue bow and we have a red stern. The compass needle is shown in the middle of the ship. We know that the end of the compass needle pointing towards north is the red end, and the one pointing towards the south is the blue end. So we have the compass needle. Now when the ship is heading north, these blue and red poles of the ship are exactly north and south of our compass needle. So being exactly north and south of the compass needle, they do not generate any deviation at all. So there is no deviation on the northerly heading. Let's now assume the vessel has moved to a northeasterly heading in this particular direction. Now the blue pole has gone northeast of the compass, and this blue pole is going to attract the red pole of our compass, and the compass is going to deviate towards east. So you have a easterly deviation. The same thing happens with the red pole. The red pole of the ship, permanent magnetism, red pole of the ship has gone to southwest of the compass, and it attracts the blue end of the compass towards it, giving the compass a easterly deviation. So you can see now on a northeasterly heading, a easterly deviation is generated. When the ship goes to a easterly heading, 090 heading, now you see the blue pole is to the east of the compass and the red pole is to the west of the compass. They are at right angles to the poles of the earth, and now in this location they generate maximum deviation. The blue pole at the bow attracts the north end or the red end of the compass towards it, and the red pole at the stern attracts the south end of the compass towards it, giving it maximum easterly deviation. When the ship heads in a southeasterly direction, the blue bow goes to southeast of the compass, and this blue bow repels the blue end of the compass needle, that is the south end of the compass needle. Similarly, the red pole of the ship at the stern repels the north end of the magnetic needle, again giving it a easterly deviation. But the magnitude of the easterly deviation starts to reduce now because the ship's poles are coming in line with the magnetic field of the earth. Maximum deviation is generated when the ship's poles are at right angles to the magnetic field of the earth, which happened on easterly heading, and minimum deviation is generated when the poles are aligned with the poles of the earth, which happened on northerly heading. If ship pole and earth pole are aligned, there will be no deviation at all, and if the ship's poles and earth pole are at right angles, there will be maximum deviation. So that's why in the southeasterly heading, the deviation is reduced now, but it is still easterly. When the ship goes on southerly heading, even though the blue pole is closer to the blue end of the compass needle and the red pole is closer to the red end of the compass needle, they are still not able to generate any deviation. The red poles are repelling, blue and blue poles are repelling, but the strength of the poles of the ship is much weaker as compared to the strength of the earth's poles. So that is why they are not able to turn the compass needle by 180 degrees. If the ship's field was more powerful, it would turn the compass needle by 180 degrees and the needle will start pointing south. But since these poles are much weaker, the magnetism of the ship is much weaker as compared to the magnetism of the earth, they are not able to generate any deviation at all. When the ship goes on southwesterly heading, you can now see that the blue pole at the bow repels the blue end of the compass needle. Similarly, the red pole at the stern of the ship repels the red end of the compass needle, generating a westerly deviation. When the ship is heading in the westerly direction, this westerly deviation becomes maximum because the poles of the ship are at right angles to the poles of the earth. The blue pole to the west of the compass needle attracts the red end towards it, generating a westerly deviation. Similarly, the red pole of the ship at the stern attracts the blue end of the compass needle, generating a westerly deviation. So maximum westerly deviation is generated on westerly heading. With the ship going on northwesterly heading, the deviation is still westerly, but the magnitude is reduced because the ship's poles are now coming in line with the magnetic poles of the earth. Coming back to north, the deviation becomes 0. So you see from 000 to 180, the deviation was easterly, and from 180 to 360 the deviation was westerly. This is what we mean by a semicircular deviation. For one semicircular, the deviation has a single name. For another semicircle, the deviation has a opposite name. So therefore, it is called as a semicircular deviation. Now, another important thing which you can see from this diagram is that these poles of the ship also affects the directive force at the compass location. What is this directive force? Directive force is the strength of the magnetic field at the compass location which makes it point towards the north direction. Now with the vessel heading on the northerly heading, you can see that the poles of the ship are matching with the poles of the earth. The earth's north pole is a blue pole and the ship structure also has a blue pole north of the compass. So this blue of the earth and blue of the ship are adding up, increasing the magnetic field. Similarly, south of the compass we have the red magnetic pole of the earth and the ship's pole is also red. So earth's red and ship's red, they also add up to the directive force. So in this particular heading, northerly heading, the directive force is increased to its maximum. When the ship goes on easterly heading, in the easterly heading, the red and blue poles of the ship are neither north of the compass nor south of the compass. They are exactly east-west of the compass. Being east-west of the compass, they do not have any effect on the directive force.